Hello, Tor Lacey here, with a reading from the online textbook An Introduction to Geology, free textbook for college-level introductory geology courses from Salt Lake Community College. And I'm going to read part of Chapter 2, Plate Tectonics. The opening photograph here, a layer of shallow ocean limestone white, has been brought to the top of a mountain by convergent forces of the severe orogeny near Sun River Canyon in Montana. So rock that was originally made thousands of feet deep in the ocean is now many thousands of feet above sea level due to plate tectonic forces. Plate tectonics, key concepts. At the end of this chapter, students will be able to describe how the ideas behind plate tectonics started with Alfred Wegener's hypothesis of continental drift. Describe the physical and chemical layers of Earth and how they affect plate movement. Explain how movement at the three types of plate boundaries causes earthquakes, volcanoes, and mountain building. So that's about as far as I'm going to go with the reading. The remainder of this stuff, for the most part, is covered in my lecture on plate tectonics. You can certainly read the entire chapter. It's well written, and there's lots of good stuff in here that will certainly deepen your understanding of plate tectonics. But I'm going to try to keep this assigned reading short. Scrolling down a bit here to look at this illustration of a map of all the known plates, their boundaries, and movements. So plates being a piece of the lithosphere, which includes the crust. Plate boundaries being the line along which two plates meet and interact. So, for example, here we have the very large Pacific plate, and then on the other side of its plate boundary, its eastern plate boundary, we have the North American plate, which extends all the way out to the middle of the Atlantic Ocean. And along this line here is the plate boundary separating the North American plate and the Eurasian plate and the African plate. So the lines that you see are plate boundaries, and then those lines are making up the borders of the individual plates. The different color codings that you see of the lines indicate the type of plate boundary it is, as is explained here in the key. And it's also important to note that we see that some plates are essentially all ocean crust, while other plates can be both continental crust and ocean crust. The plates are thicker than just the crust, and they include the uppermost part of the mantle below. Grouped together, that is considered to be the lithosphere, and that will be discussed here in the reading as well as in the lecture. Revolution is a word usually reserved for significant political or social changes. Several of these idea revolutions forced scientists to re-examine their entire field, triggering a paradigm shift that shook up their conventionally held knowledge. Charles Darwin's Book of Evolution on the Origin of Species, published in 1859, Gregor Mendel's discovery of the genetic principles of inheritance in 1866, and James Watson, Francis Crick, and Rosalind Franklin's model for the structure of DNA in 1953 did that for biology. Albert Einstein's relativity and quantum mechanics concepts in the early 20th century did the same for Newtonian physics. The concept of plate tectonics was just as revolutionary for geology. The theory of plate tectonics attributes the movement of massive sections of Earth's outer layers with creating earthquakes, mountains, and volcanoes. Many Earth processes make more sense when viewed through the lens of plate tectonics. Because it is so important in understanding how the world works, plate tectonics is the first topic of discussion in this textbook. Alfred Wegener's continental drift hypothesis. Alfred Wegener, 1880 to 1930, was a German scientist who specialized in meteorology and climatology. His knack for questioning accepted ideas started in 1910, when he disagreed with the explanation that the Bering Land Bridge was formed by isostasy, and that similar land bridges once connected the continents. After reviewing the scientific literature, he published a hypothesis stating the continents were originally connected and then drifted apart. While he did not have the precise mechanism worked out, his hypothesis was backed up by a long list of evidence. Early evidence for continental drift hypothesis. Wegener's first piece of evidence was that the coastlines of some continents fit together like pieces of a jigsaw puzzle. People noticed the similarities in the coastlines of South America and Africa on the first world maps, and some suggested the continents had been ripped apart. Antonio Snyder Pellegrini did preliminary work on continental separation and matching fossils in 1858. An illustration from Pellegrini here. What Wegener did differently was synthesize a large amount of data in one place. He used true edges of the continents based on the shape of the continental shelves. This resulted in a better fit than previous efforts that traced the existing coastlines. Wegener also compiled evidence by comparing similar rocks, mountains, fossils, and glacial formations across continents. For example, the fossils of the primitive aquatic reptile Mesosaurus were found on the separate coastlines of Africa and South America. Fossils of another reptile, Lithosaurus, were found on Africa, India, and Antarctica. He pointed out these were land-dwelling creatures and could not have swum across an entire ocean. Here's a map summarizing that last paragraph. Opponents of continental drift insisted transoceanic land bridges allowed animals and plants to move between continents. The land bridges eventually eroded away, leaving the continents permanently separated. The problem with this hypothesis is the improbability of a land bridge being tall enough and long enough to stretch across a broad open ocean. More support for continental drift came from the puzzling evidence that glaciers once existed in normally very warm areas in southern Africa, India, Australia, and Arabia. These climate anomalies could not be explained by land bridges. Wegener found evidence when he discovered tropical plant fossils in the frozen region of the Arctic Circle. As Wegener collected more data, he realized the explanation that best fit all climate rock and fossil observations involved moving continents. Proposed mechanism for continental drift. Wegener's work was considered a fringe scientific theory for his entire life. One of the biggest flaws in his hypothesis was an inability to provide a mechanism for how the continents moved. Obviously, the continents did not appear to move, and changing the conservative minds of the scientific community would require exceptional evidence that supported a credible mechanism. Other proto-continental drift followers used expansion, contraction, or even the moon's origin to explain how the continents moved. Wegener used centrifugal forces and precession, but this model was proven wrong. He also speculated about seafloor spreading with hints of convection, but could not substantiate these proposals. As it turns out, current scientific knowledge reveals convection is one of the major forces driving plate movements along with gravity and density. Spend a moment with this animation about convection, a very important concept for plate tectonics. Development of plate tectonic theory. Wegener died in 1930 on an expedition in Greenland. Poorly respected in his lifetime, Wegener and his ideas about moving continents seemed destined to be lost in history as fringe science. However, in the 1950s, evidence started to trickle in that made continental drift a more viable idea. By the 1960s, scientists had amassed enough evidence to support the missing mechanism, namely seafloor spreading, for Wegener's hypothesis of continental drift to be accepted as the theory of plate tectonics. Ongoing GPS and earthquake data analysis continue to support this theory. The next section provides the pieces of evidence that helped transform one man's wild notion into a scientific theory. Mapping of the ocean floors. In 1947, researchers started using an adaptation of sonar to map a region in the middle of the Atlantic Ocean with poorly understood topographic and thermal properties. Using this information, Bruce Heezen and Mary Tharp created the first detailed map of the ocean floor to reveal the Mid-Atlantic Ridge, a basaltic mountain range that spanned the length of the Atlantic Ocean, with rock chemistry and dimensions unlike the mountains found on the continents. Initially, scientists thought the ridge was part of a mechanism that explained the expanding Earth or ocean basin growth hypothesis. In 1959, Harry Hess proposed the hypothesis of seafloor spreading, that the mid-ocean ridges represented tectonic plate factories, where new oceanic plate was issuing from these long volcanic ridges. Scientists later included transform faults perpendicular to the ridges to better account for varying rates of movements between newly formed plates. When earthquake epicenters were discovered along the ridges, the idea that earthquakes were linked to plate tectonics movement took hold. This video here about Mary Tharp's maps is excellent, so pause my reading and be sure to enjoy that. I think it's well done. I'll continue here. Seafloor sediments measured by dredging and drilling provided another clue. Scientists once believed that sediment accumulated on the ocean floors over a very long time in a static environment. When some studies showed less sediment than expected, these results were initially used to argue against continental movement. With more time, research discovered these thinner sediment layers were located close to the mid-ocean ridges, indicating the ridges were younger than the surrounding ocean floor. This finding supported the idea that the seafloor was not fixed in one place. Paleomagnetism is excellent evidence to support plate tectonics, but it's a little bit complicated, so I'm going to skip over that, and I'm going to skip over the Wadati-Benioff zones as well. But again, you can certainly read these on your own to gain a deeper understanding of this stuff. Be sure to take the quizzes, which will help reinforce what you've learned. Now I'm going to get into layers of the Earth. In order to understand the details of plate tectonics, it is essential to first understand the layers of the Earth. First-hand information about what is below the surface is very limited. Most of what we know is pieced together from hypothetical models and analyzing seismic wave data and meteorite materials. In general, the Earth can be divided into 3 layers based on chemical composition and physical characteristics. So this illustration here is showing the layers of the Earth. Physical layers include the lithosphere and asthenosphere. Chemical layers are crust, mantle, and core. So there are 2 ways of thinking about the structure of Earth. One based on the chemical composition, and those are terms that you probably are familiar with. The crust, which is the uppermost layer, the mantle, and the core. But the Earth could also be divided into layers based on the physical properties of the Earth. And these terms include the inner core, outer core, mesosphere, asthenosphere, and lithosphere. And I'm going to discuss both here. Chemical layers. Certainly the Earth is composed of a countless combination of elements. Regardless of what elements are involved, 2 major factors, temperature and pressure, are responsible for creating 3 distinct chemical layers. Crust. The outermost chemical layer, and the one we currently reside on, is the crust. There are 2 types of crust. Continental crust has a relatively low density and composition similar to granite. Oceanic crust has relatively high density, especially when cold and old, and composition similar to basalt. The surface levels of crust are relatively brittle. The deeper parts of the crust are subjected to higher temperatures and pressure, which makes them more ductile. Ductile materials are like soft plastics or putty. They move under force. Brittle materials are like solid glass or pottery, and they break under force, especially when it is applied quickly. Earthquakes generally occur in the upper crust and are caused by the rapid movement of relatively brittle materials. The base of the crust is characterized by a large increase in seismic velocity, which measures how fast earthquake waves travel through solid material. Called the Mohorovici discontinuity, or MOHO for short, This zone was discovered by Andrija Mohorovici in 1909 after studying earthquake wave paths in his native Croatia. The change in wave direction and speed is caused by dramatic chemical differences in the crust and mantle. Underneath the oceans, the Moho is roughly 5 kilometers below the ocean floor. Under the continents, it is located about 30 to 40 kilometers below the surface. Near certain large mountain building events known as orogenies, the continental Moho depth is doubled. The mantle sits below the crust and above the core. It is the largest chemical layer by volume, extending from the base of the crust to a depth of about 2,900 kilometers. Most of what we know about the mantle comes from seismic wave analysis, though information is gathered by studying Ophelites and Xenoliths. Ophelites are pieces of the mantle that have risen through the crust until they are exposed as part of the ocean floor. Xenoliths are carried within magma and brought to the Earth's surface by volcanic eruptions. Most xenoliths are made of peritotite, an ultramafic class of igneous rock. Because of this, scientists hypothesize most of the mantle is made of peritotite. Here we have a photograph of peritotite, which is essentially olivine, and you've learned about olivine in class. Core, the core of the Earth, which has both liquid and solid layers, and consists mostly of iron and nickel, and possibly some oxygen. Scientists looking at seismic data first discovered this innermost chemical layer in 1906. Through a union of hypothetical modeling, astronomical insight, and hard seismic data, they concluded the core is mostly metallic iron. Scientists studying meteorites, which typically contain more iron than surface rocks, have proposed the Earth was formed from meteoric material. They believe the liquid component of the core was created as the iron and nickel sank into the center of the planet, where it was liquefied by intense pressure. Physical layers. The Earth can also be broken down into 5 distinct physical layers based on how each layer responds to stress. While there is some overlap in the chemical and physical designations of layers, specifically the core, mantle, boundary, there are several differences between the two systems. Lithosphere. Lithos is Greek for stone, and the lithosphere is the outermost physical layer of the Earth. It is grouped into 2 types, oceanic and continental. Oceanic lithosphere is thin and relatively rigid. It ranges in thickness from nearly 0 in new plates found along mid-ocean ridges to an average of 140 kilometers in most other locations. Continental lithosphere is generally thicker and considerably more plastic, especially at the deeper levels. Its thickness ranges from 40 to 280 kilometers. The lithosphere is not continuous. It is broken into segments called plates. A plate boundary is where 2 plates meet and move relative to each other. Plate boundaries are where we see plate tectonics in action, mountain building, triggering earthquakes, and generating volcanic activity. A simplified map of Earth's major plates here. Asthenosphere. The asthenosphere is the layer below the lithosphere. Astheno means lacking strength, and the most distinctive property of the asthenosphere is movement. Because it is mechanically weak, this layer moves and flows due to convection currents created by heat coming from the Earth's core cause. Unlike the lithosphere that consists of multiple plates, the asthenosphere is relatively unbroken. Scientists have determined this by analyzing seismic waves that pass through the layer. The depth of which the asthenosphere is found is temperature dependent. It tends to lie closer to the Earth's surface around mid-ocean ridges and much deeper underneath mountains and the centers of lithospheric plates. I'm going to skip over mesosphere and inner and outer core. Again, do the quiz to help you better understand the material, or at least check for your understanding of material, and then you can go back and review if you missed any of the questions. Plate tectonic boundaries. At passive margins, the plates don't move. The continental lithosphere transitions into oceanic lithosphere and forms plates made of both types. A tectonic plate may be both may be made of both oceanic and continental lithosphere connected by a passive margin. North and South America's eastern coastlines are examples of passive margins. Active margins are places where the oceanic and continental lithospheric tectonic plates meet and move relative to each other, such as the western coasts of North and South America. This movement is caused by frictional drag between the plates and differences in plate densities. The majority of mountain building events, earthquake activity, and active volcanism on Earth's surface can be attributed to tectonic plate movement at active margins. This illustration here summarizes the three types of plate boundaries: transform, divergent, and convergent. Along this continental margin here, we have an example of an active continental margin because a plate boundary separates the continental lithosphere from the oceanic lithosphere. In the simplified model, there are three categories of tectonic plate boundaries. Convergent boundaries are places where plates move toward each other. At divergent plate boundaries, the plates move apart. At transform boundaries, the plates slide past each other. Again, complete the quiz, and I will stop the reading here. Feel free to continue if you have the time and desire to do so. Thank you for listening.